All right, so solving an equation that includes a radical. Now, what we're going to do here, and I'm going to do just a quick little note, is that maybe before we've done this type of equation, we've seen something like x squared is equal to 9. And when we wanted to get x by itself, we would do the square root property, and that would give us x is equal to positive negative 3. Positive negative because, again, quadratics, when you're looking at their graph, they have generally a left and a right side of the y-axis, and so we might have negative 1, 2, 3 on this side, 1, 2, 3 on that side, and those are the two times where it intersects at y of a y value of 9. Now, what we're doing here is we already have a radical. There's already a square root there. So since we've already got a square root, suppose we had square root x equal to, any number here, I'll just put 10. And we wanted to make that just x, then what we could do is now square it. But then we would also square the other side as well. Now, when you do the square of a square root, it will simplify to just x. And so think of these as inverses. So just like adding and subtracting undo each other, and multiplication and division undo each other, square roots and squares undo each other. So that's what we're going to do with this one. Again, that's just a quick little intro to the strategy we're going to take when dealing with radicals. Now, the index here is a little 2. We usually don't write it, but we do say square root. And again, to get rid of the square root, we're going to do the inverse, which is we're going to square it, which means we'll also need to square the right side. And as I mentioned just a moment ago, that is going to get rid of everything except for the 10w minus 16. That radicand or the expression comes out. Now we got w squared. And now what we want to do is isolate 0 on one side or the other. We're going to move 10w and minus 16 over to the right side. So this will isolate our 0. And we've now got w squared minus 10w plus 16. And we should now have a trinomial that can factor into two binomials of w squared. Excuse me, w times w. And then again, if you're looking for what two numbers multiply to give you positive 16, but also add to give you negative 10. Again, take some time to think about it, but you will eventually find that it's 8 times 2, where you have a negative 8 and a negative 2. And so that would lead to us factoring negative 8 and negative 2. And now use the zero product property. W minus 8 is equal to 0. W minus 2 is equal to 0. And we'll get our two solutions. Now, when you do squaring, you generally want to check to make sure that you don't have any extraneous answers. Again, going back to the idea that quadratics generally have a sort of a left side and a right side to the y-axis. So they're generally trying to help us find two solutions, maybe something on the left side, the right side. And so that may lead to what's known as extraneous solutions. But we're going to check these. So when we plug in 8, when we plug in 2, again, this is just our check. We'd have 10 times 8 minus 16. Does that all equal to 8? That would be square root of 80 minus 16, which is the square root of 64. And you can see that the square root of 64 is 8, so that checks out. But let's also check the 2. We'd have 10 times 2 minus 16, and does that equal 2? That would be 20 minus 16, which is square root 4, which does equal 2. So we're good. These are both two good solutions. You could also look at the graph. You could think of that original equation, again, just to make this a little bit neater. That was the original equation we had, and if you were to graph just the left side, it would look something like sort of like the parent function. That's a radical. And if you graph again, think of this as y equal to, and just graph that, And then if you graph the right side, again, just maybe graphing like y is equal to w, that would be a straight line. Something like that. And you would see that at 2 and at 8, it intersects. The two lines intersect each other. And that's just one way to think about it, but we're good. We've got our two solutions. Here's another one where, again, we want to be able to do the squaring to get rid of our radical, but we first need to isolate the radical. So we'll add 1, w plus 14, which equals to 7. We'll square both sides. This will free up our radicand. So we've got w plus 14. Now, don't forget to square the 7, so we've got 49. Then we'll minus 14. And we get w is equal to 35. And again, you can plug that in and you can check your answer, but that's something that I did ahead of time, and it does work. Again, if you were checking your answer like in Desmos, graph the equation y is equal to square root w plus 14 minus 1. And what that would look like is something like this. And then graph y is equal to 6. And you would see that it does a horizontal or a constant line, where right there is the point of intersection at I guess it would be 35. I'm not going to do it, but it's, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 35 is when you would see that they intersect each other. Okay, all right, let me do this one here. So same thing, we want to try to get rid of that exponent. It is a 3/2, and we want to find out when does this ever equal to -2. And so one way to get rid of this is, since we've got a 3 over a 2, you could raise this to the power of 2. And maybe even to help as a 1. And what that's going to do is that's going to slash out the 2 and the 2. And that would help you get rid of your rational power. So again, maybe I'll put this together. Okay, remember with our exponent rules, we multiply numerator, denominator. So we'd have 6 over 2. But that reduces to just 3. And then now that we have a 3, what we could do then is do the cubed root. Okay. Oh, and sorry, one thing I forgot. Right? Whatever we do to the left side, we got to do the right side. I've also got to square this as well too. So it's really easy to forget, but that's what we practice. So this gives us a 4. And then we would do the cubed root from the left side, cubed root to the right side. Again, these two offset each other. So we're left with just the y minus 1. And then we've got the cubed root of 4. Then we add our 1 to both sides, and we got y is equal to the cubed root of 4 plus a 1. But now you want to plug it in to make sure that it does check out. And one of the things about this graph is that if you were to graph the left side, it looks something like that. And if you were to graph the right side at -2, you can see that there's no point of intersection. And so there really is no solution for this one. And if we were to check our answer and go back to the original equation, which was this, when does it ever equal -2? And we plug this here in for y to check our answer. Here's what would happen. You would have the the cubed root of 4 plus 1 minus 1. 3/2 is equal to -2. Now these two would be gone. Then we would have the cubed root of 4, 3/2 is equal to -2. Again, we're trying to see if the left side ever comes out to be equal to -2. Now, what we could do here is write this as 4 to the 1/3 power. That's the cubed root is the same thing as 4 to the 1/3 power. And now look what's going to happen here. These 3's, this 1/3 and 3/2, they multiply to give us 3 over 6, but then that reduces to 1/2. And then 1/2, 4 to the 1/2 power is the same thing as the square root of 4. But then this leads to 2, but that does not equal -2. So this one, short story, is no solution. All right, last one. Again, we'll take the same idea that we just had a moment ago, where we've got 3/5 as our exponent. And to start getting rid of this, we can take the entire left side, which means we're going to do it to the same thing to the right side, and raise it to the power of 5. Raise it to the power of 5. Again, if it helps to see that as over 1. But notice that the 5 and the 5 will divide out, which will leave us with just a 3. V minus 9 cubed, and then 2 to the power of 5. 2 times 2 times 2 times 2 times 2, 5 of them gives us 32. Then we will do the cubed root, again, because we want to get rid of that cube. And then we'll also do the cubed root to the right side as well. This will leave us v minus 9, and then we've got the cubed root of 32. And if they ask you to simplify this, now here's the answer that we're trying to head to. Is like, whoa, how do we get down to that? You can see that we're going to add the 9 over. But when it comes to simplifying radicals, in this case where the index is a 3, what I would recommend doing is taking 32 and doing a factor tree. This is 2 times 16. This is 2 times 8. And then 8 is 2 times 2 times 2. And notice that we have a 2 times a 2 times a 2 times a 2 times a 2. And right here is a trio. And so we could write this as 2 cubed and 2 squared. And so when we break this apart, when we take this 32, it's the same thing as the cubed root of 2 cubed times 2 squared. And now we'll break this apart into 2 cubed to the index 3 times 2 squared to the index 3. But any time that the index and the exponent here match, then that's okay. You can think of it as, well, it would be 2. It just simplified to just be a 2. Now the other one, there's really nothing we can do about it since the index and the power don't match. So we'll leave it as cubed root of 4. And again, we add our 9 over, and we add our 9 over. We get v is equal to, again, it's going to be 2 cubed root of 4 plus 9. And that's what matches our answer there. All right, so that would be